Hello and welcome to another video on our unit covering vectors and parametric equations. Today I'm going to introduce the definition of the dot product and talk about some of the geometric applications of vector operations. So we are going to have two definitions of the dot product. Here is the first. This says that vector v dot vector w equals the x component of v times the x component of w plus the y component of v times the y component of w. So this should sort of make sense that the dot product, we're going to use a dot as the symbol here. And over here is another definition of the dot product, that vector v dot vector w is going to be the magnitude of v times the magnitude of w times the cosine of the angle between them. So theta in this case is the angle between the vectors. So let me just do a quick computational example. I've got vector v here and vector w, so I'm going to compute the dot product. I'm going to compute v dot w. So that's going to be, I'm going to multiply the x components together. 2 times negative 5. I'm going to add that to multiplying the y components together. That to 5 times 7. So that's going to give me negative 10 plus 35, which is 25. So the dot product of v and w is 25. So a couple of things to take note of here, that the dot product takes two vectors and produces a scalar. So the sort of the result, the outcome of doing one vector dot another vector is you are going to produce a scalar. Now, these two definitions, first they look different, but they're identically the same. So we need to figure out why these two definitions are the same. And then also we need to figure out, like, what is this dot product? I'm just sort of defining this operation, and it seems like I'm just making this up out of thin air. But these definitions are not random, and they have very strong geometric consequences in 2 dimensions, and 3 dimensions, and 4 dimensions, and so on and so on. So it's going to allow us to do a lot of very powerful thinking geometrically with vectors in any number of dimensions that we want, and it just is going to open up the door to doing a lot of cool applications. But right now this sort of seems very black box. So I just wanted to introduce the formulas to you, do a couple of computations, and we're going to spend our time in class really thinking about what the dot product means, both algebraically and geometrically, and sort of all of the consequences with working with vectors and the dot product, and try to discover as much as we can. So this video is sort of bland and dry in the sense that we're just going to be doing some computations, and everything just seems sort of arbitrarily defined at this point. So I just want to do the other version of the dot product to show you that if I take the same two vectors, vector v and vector w, I didn't change them. So it shouldn't matter what version of the dot product that I use. Okay, so sort of in this version of the dot product, I've got to find the magnitude of v. So that's going to be the length of vector v. That'll be 2 squared plus 5 squared, the square root of that. The length of vector v is root 29. The magnitude of vector w is going to be negative 5 squared plus 7 squared, the square root of that. So I believe that is root 74. So I found the magnitude of v and the magnitude of w. But now to compute the dot product here, I need to multiply the magnitudes of my vectors, but also multiply by the cosine of the angle between them. So for that, I'm going to sketch a picture. So I'm going to sketch vector v here. So there's vector v. I'm going to sketch vector w. So theta is going to be this angle in here, the angle that is created, that is in between the two vectors. So in order to do that, I'm going to have to do some basic trigonometry here. If I sort of draw down a right triangle here, draw down a right triangle here, I know that these three angles are going to add up to 180 degrees, and I can compute what these two acute angles are. They're reference angles and some right triangles here, so I just need to do some trig. So this angle over here, that's going to be the tan inverse of 5 over 2. This angle right in here is going to be the tan inverse of 7/5, and I know that the tan inverse of 5 halves plus the tan inverse of 7/5 plus theta is going to equal 180, so if I want to find theta, I can just do 180 minus the sum of those two angles, and that's going to give me theta. So probably the hardest part of computing the dot product this way is typing everything in the calculator correctly. So that's why I screenshot the calculator here. So the root 29, there's the magnitude of v. Root 74, that's the magnitude of w. And then I've got this cosine of theta, where theta is the angle in between the vectors. And theta is 180 minus, I would need some parentheses here to make this all work out right. So it's 180 minus the tan inverse of 5 halves minus the tan inverse of 7/5. So I've got that all right in my calculator. Then notice I'm working in degrees here. So I had to make sure that I was in degree mode, and when you type this in the calculator exactly, I haven't rounded anything off. I see that the dot product is indeed, for this example again, 25. So that checks out with the other version of the dot product. But again, this is all very black box, very mysterious right now. Like, why am I doing this? What do these computations mean? We really need to investigate these ideas further. This is just sort of to get us some definitions. We can do some computations, look at a bunch of examples, and then sort of tease out all of the geometric consequences. So now another thing that hasn't come up yet in class that I wanted to just talk about real quick is just the geometry of vector addition here. So we've talked about vector operations. I could add vectors v and w together rather quickly. I would get 3, just add the x components and add the y components, 3, 4. So the sum of those two vectors is a new vector whose components are 3 and 4. But I just wanted to draw a picture to show sort of geometrically what's happening here. It's actually pretty interesting. So if I sketch out the vector -2, 3, look about like there, there's v. If I sketch out w, 5, 1, I get like that vector right there. So if I want to sort of geometrically see what's going on here with this addition, I could sort of just reposition this vector w. When the x component is 5 and the y component is 1, I didn't have to situate this at the origin. So I'm going to draw vector w, sort of align the tip of vector w with the tail of vector w with the tip of vector v. So starting from here, I'm going to draw 5, 1. So go over 5, up 1. That puts me right there. And then notice where I ended up there when I align the tip of one vector with the tail of the other, and I sort of draw that picture there. If I connect that from the origin, look at that. There's the vector 3, 4 right there. And then what's more, if I just sort of completed the picture, if I drew in this segment right here, look, that actually creates a parallelogram. So that's sort of the parallelogram that's spanned by these two, by this vector v and vector w, creates this nice parallelogram, and then the diagonal of that parallelogram, that's the result when you add the two vectors together. So even with something simple like vector addition, there's this nice geometric sort of way to arrange the vectors in the plane to see the result of the addition. So this works with subtracting vectors. There's all sorts of pictures we're going to be able to draw to see what the dot product is actually computing. So there's a lot of geometry to sort of think about, and there's a lot of interesting questions that come up here, like this parallelogram that I've sort of drawn here. Like, what is the area of this parallelogram, and what does that represent in terms of what we're doing here mathematically? Just all sorts of great questions that we're really going to investigate further. So I hope you enjoyed this video, and we'll see you in class tomorrow.